This is a Key Stage 3 video for the topic light and sound, looking at sound, and it's kind of an introduction to the properties of sound. So sound is described as a longitudinal wave, represented really well with a slinky because it shows that the particles don't keep moving. They just, one particle is bumped, it bumps into another one, that bumps into another one, transferring the energy from one place to another. So the particles don't really move that far, they just kind of transfer that energy across them, okay? Sound needs particles to travel, unlike light, which can travel without particles, and it travels because those particles hit into each other. They transfer the sound energy. This means that sound cannot travel through a vacuum. Okay, a vacuum is a space where there are no particles. Space is a vacuum, okay? Out there in the universe, space is a vacuum. So in reality, when they say in space no one can hear you scream, it is true, okay? So you can't hear anything in space because there's no particles to transfer the sound. However, the light from the sun gets to us on Earth because light doesn't need particles to travel. The speed of sound is much slower than the speed of light at about only 340 meters per second. Okay, that's why we can see a firework and then hear the bang from it. That's why we see the lightning and then hear the crash of the thunder afterwards, because sound is a lot slower than light. So more about the fact that sound needs particles to travel. We've got the experiment with the bell jar. So here we have a bell inside a bell jar, and we set the bell to ring, and then we attach it to a vacuum pump which removes the particles from the bell jar. And as we remove those particles using the vacuum pump, we notice that the sound of the bell gets much quieter because there aren't the particles there to transfer the sound to our ears out of the bell jar. And then once we've turned the vacuum pump off and we allow the air particles to gradually go back into the bell jar, we hear the bell gets much louder again. And that's proving that sound needs particles in order to travel. Okay. We also did the experiment where we put our head on the desk, we had the tuning fork struck on the table and then placed on the table, and it's much easier to hear that sound still going through the vibrating particles of the solid table than it is when you lift your head up. You can't hear it through the air because those particles are further apart. Okay, so showing again that the sound travels much better where there's lots of particles in the table. And the last thing we're going to look at in this video is the speed of sound, okay, and that relates back to what I just said about the tuning fork. So again, reiterating that sound needs particles to travel, it can't travel through a vacuum, and we've got a graph here which we can make lots of conclusions about. So we can see, if I just look a bit closely here, we can see that air at 0 degrees, the speed of sound travels slower than air at 30 degrees, okay, the first two bars on that graph. And that's basically saying that if the particles have got more energy, which they would at 30 degrees C, they're moving faster, therefore transferring the sound faster. If we then look at the difference between the air, the water and the solid, we can see that the particles are closer together in a solid, therefore the sound is able to transfer from one particle to another really easily. The particles in the water would be moving around, so it would kind of redirect the sound in all directions, therefore losing some of that speed. The particles aren't organised like they are in a solid, and the particles in the air are much more spread apart, big gaps between them, therefore the sound travels even slower. Okay, and then we've got this last one that says that, let's zoom in and have a look, that sound travels faster in steel than it does in concrete, okay? And that's to do with the density of steel compared to concrete. So steel is much denser, that means that the particles are even closer together, really densely packed together compared to the concrete, and that again, close packing together of the particles means that the sound can travel much faster. So let's just see what the card says, okay? So sound needs particles to travel, cannot travel through a vacuum, therefore makes sense that sound travels faster when particles are close together, such as a solid, and even more so when that solid is very dense, the particles are packed closely together. Temperature can also affect the speed of sound, as when particles are heated, they move faster. Okay, therefore more chance of collision. Hope you found that useful. Thank you.